Since Galileo Galilei first turned a telescope toward the heavens in 1609, humanity has embarked on a timeless journey to search for signs of life beyond Earth. Yet in recent years, research has brought astonishing discoveries, opening an entirely new vision of what might be possible. One of the most remarkable findings came from NASA's Cassini mission. Plumes of icy water erupting from Saturn's moon Enceladus, rich with complex organic molecules, the essential building blocks of life. But that's not all. New theories about subsurface oceans on Europa, Jupiter's enigmatic moon, supported by data from the Hubble Space Telescope, promise to reveal more about the hidden environments that may nurture life beneath the ice. At the same time, scientists have identified habitable zones on planets beyond our solar system. Worlds like Kepler 452b, whose atmosphere and temperatures mirror those of Earth. We have uncovered fascinating clues, but the question remains, does life truly exist out there? The evidence is growing clearer, and the answer, perhaps, is closer than we ever imagined. To truly understand where life might exist, we must look beyond Earth-like environments and explore conditions utterly different from our own, where the laws of science themselves might behave in unimaginable ways. The first thing scientists look for when observing a distant planet is the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist, a key ingredient for life as we know it. This concept comes from the belief that life requires water to develop. And water can only remain in liquid form within a specific temperature range. In our solar system, planets like Venus and Mars have extreme conditions. Too hot or too cold to sustain liquid water, making them inhospitable. However, planets such as Kepler 452b, a super-Earth located about 1,400 light-years away, exist within the habitable zone of a Sun-like star. Such worlds could potentially support life, provided they have liquid water. But this raises a deeper question. Is liquid water alone enough? Recent studies suggest that life might require more than just the right temperature and water. Carbon forms the backbone of all complex organic molecules, from proteins to DNA, and it is the foundation of every living structure. Carbon chains allow the creation of cells, the basic building blocks of life. For this reason, carbon is considered the essential element for life as we know it. However, in the search for extraterrestrial life, one critical question emerges. Could life exist without carbon? Scientists have begun exploring alternative elements that might support life. One such candidate is silicon, the element directly beneath carbon on the periodic table. Silicon can form chemical bonds similar to carbon, leading many researchers to speculate that alien life might be based on silicon instead. Yet silicon's molecular structure lacks the flexibility of carbon. Its bonds are less adaptable, making it difficult to form the complex dynamic structures associated with advanced life. Still, that doesn't mean silicon-based life is impossible. Could there be life in worlds utterly unlike Earth? One fascinating discussion centers on the possibility of non-traditional life thriving in exotic atmospheres. For example, Venus, with its clouds of sulfuric acid and surface temperatures hot enough to melt lead, would seem utterly inhospitable. In addition, life may exist not only on the surface of planets but also in the temperate layers of the atmospheres of planets with extreme conditions. Scientists have suggested that life might develop on a planet with a dense atmosphere. Not from the surface, but within the higher cloud layers, where water molecules could exist without being destroyed by the planet's surface heat. To find the answer to this question, scientists have had to expand the scope of the search for life. They are not only looking for traces of water or oxygen, but also for methane, phosphine, and complex organic molecules that may appear in the atmospheres of distant planets. These gases could be products of biochemical processes we do not yet fully understand, or they could be traces of life. One of the latest discoveries relates to the presence of phosphine in the atmosphere of Venus, a gas that is very difficult to form under natural conditions without the involvement of biological processes. This has made scientists reconsider the possibility that life could exist in an environment as extreme as Venus. Could life exist in a form unlike Earth's within this special atmospheric environment? The answer is gradually being revealed through clues found in research, and these discoveries could completely change the way we perceive life in the universe. If you love this topic, subscribe to WUFO now so you won't miss the next discoveries. When we turn our gaze toward distant planets in the Goldilocks zone, hundreds of millions of kilometers from Earth, there are two icy moons, Europa, the moon of Jupiter, and Enceladus, the moon of Saturn. These icy worlds may hold one of the greatest secrets in the quest to find life beyond Earth. Both of these moons share one remarkable feature. Beneath their thick layers of ice are vast oceans of liquid salt water. Environments that could be suitable for life, this is a completely new and fascinating discovery, opening many opportunities for science. Could we find life in these oceans? The answer may lie just beneath the eternal ice, where temperatures and conditions are beyond imagination. We begin with Europa, the moon of Jupiter, where data collected from the Galileo spacecraft has provided clear evidence of a global ocean beneath its thick ice. Believed to be as deep as 100 kilometers, this ocean may harbor life we have never imagined. What makes Europa special is the existence of liquid water beneath the ice. An ideal condition for life, even though it is far from the sun. The question is, how does Europa keep its water in liquid form in a cold environment without sunlight? Tidal heating, a phenomenon caused by the interaction between Europa and Jupiter. As Europa orbits Jupiter, the planet's immense gravity creates friction, heating the icy crust and maintaining subsurface temperatures warm enough to keep the water liquid. The hydrothermal vents at Europa's ocean floor could provide energy for chemosynthetic life, similar to Earth's deep-sea ecosystems, where no sunlight exists, but life thrives through chemical reactions. Cooled microorganisms exist at the bottom of this ocean, living on chemical energy instead of sunlight. Meanwhile, on Enceladus, scientists have observed massive plumes of water called geysers, erupting from cracks near the moon's south pole. The molecules in these plumes, analyzed by the Cassini spacecraft, not only confirmed the presence of liquid water, but also detected organic compounds, particularly hydrogen, a strong indication that hydrothermal activity is occurring beneath the surface of Enceladus. The presence of hydrogen may indicate that life exists within this ocean, with methane-producing microbes thriving on hydrothermal energy. In addition, studies have shown that Enceladus's ocean is alkaline, a chemical environment highly favorable for the formation of prebiotic molecules while Europa and Enceladus offer a fascinating vision of life beneath their frozen oceans. We may have to completely rethink our understanding when confronting Titan, Saturn's largest moon. Unlike Jupiter's icy moons, Titan challenges every traditional definition of life in the universe. There is no liquid water here, but there is something else, liquid methane. Titan is not just a strange world, but one that completely breaks the model of life as we know it. Could life exist in a completely different solvent, not water, but methane? Titan is the only moon with a thick atmosphere, composed mainly of nitrogen and methane. This atmosphere is unlike any other in the solar system. The surface temperature of Titan is extremely cold, around -179 degrees Celsius, causing water to freeze solid. However, what's remarkable is that probes like Cassini have confirmed the existence of rivers, lakes, and seas on Titan's surface. But these lakes are not made of liquid water like those on Earth, but of methane and ethane, two liquids that exist at very low temperatures. This not only creates a strange environment, but also opens up a new concept of the liquid cycle. On Titan, liquid methane evaporates and forms methane clouds, which then rain down into lakes and rivers. This system functions much like Earth's water cycle, but with methane replacing water. Essentially, Titan is a frozen version of early Earth, a place containing all the ingredients needed to trigger prebiotic chemistry, but without water. Tholins, a type of complex organic compound, have also been found on Titan's surface. They are formed when ultraviolet light and cosmic rays react with methane and nitrogen in the atmosphere. This makes Titan a unique chemical world, resembling an early version of Earth, but without water. Instead, liquid methane serves as the main liquid in Titan's biological cycle. On Earth, water is the ideal solvent for life because it can dissolve many compounds and support key chemical reactions. But methane and ethane are nonpolar, which prevents them from dissolving compounds the way water does. However, under Titan's extremely low temperatures, liquid methane can act as a stable solvent for complex molecules, capable of supporting life. To understand this better, astrochemists have modeled molecules called azotosms, potential cell membranes that could sustain life in liquid methane. Exosomes are made of nitrogen instead of lipids, like cells on Earth. This introduces a completely new possibility in astrobiology, that life on Titan could develop not from water, but from methane and ethane. Could these molecules self-assemble into complex structures capable of sustaining life in a cold, oxygen-poor environment? If life exists on Titan, it would not breathe oxygen or need water as we imagine. Instead, life on Titan could use the hydrogen in its atmosphere and organic molecules to produce energy in a cycle completely different from that of organisms on Earth. Titan challenges every definition we have of life. It forces us to abandon the boundaries we once believed, that life must depend on water, oxygen, and moderate temperatures like Earth's. The exploration of Titan is not simply a search for life. It is a journey to discover the limits of life in the universe. How can we confirm or reject the existence of extraterrestrial life on distant planets, tens or even hundreds of light years away? The answer does not lie in theories or assumptions, but in unprecedented advanced technologies that open a window for us to peer through the universe and search for signs of life from afar. The ability to search for extraterrestrial life has now achieved a breakthrough with the James Webb Space Telescope, JWST. JWST operates by observing light when planets pass through the atmospheres of stars in distant star systems. When the light from a star passes through a planet's atmosphere, molecules within it absorb specific wavelengths of light. The analysis of these absorbed wavelengths allows scientists to determine the exact chemical composition of the planet's atmosphere. This opens the possibility of detecting chemical fingerprints that help us identify biosignatures, biological traces that may indicate life. The extreme sensitivity and analytical capability of JWST in the infrared range will help scientists search for traces of life. Even in the atmospheres of planets located far across the universe that we have never been able to reach. When we cannot approach distant planets, studying life in outer space environments becomes the key. The International Space Station, ISS, is a permanent space biology laboratory where experiments in microgravity and intense radiation have helped us better understand the biological limits of life in the harsh environment of space. One of the most important experiments conducted on the ISS is the EXPOSE program by the European Space Agency, ESA. This experiment placed extremophile microorganisms in a microgravity environment and exposed them directly to cosmic radiation and the vacuum of space. The results were surprising. Many species of bacteria, such as Bacillus subtilis and Deinococcus radiodurans, were able to survive and even grow after being directly exposed to space for long periods. These experiments reinforce the theory of panspermia, the possibility that life can spread between planets through meteorite fragments. If bacteria on Earth can survive in space, could life on Europa or Titan have come from elsewhere, or been carried there by falling meteorites? These questions not only change our perception of the universe, but also provide important clues about extraterrestrial life. Space experiments help us better understand the ability of life to exist in extreme environments, opening a path for exploring other planets with similar conditions. However, an important lesson about the survival potential of life lies right beneath our feet. In fact, organisms that live in extremely harsh environments on Earth are providing us with valuable clues about the possibility of life existing in extraterrestrial environments that seem impossible to survive. So, could life develop in extreme environments we have never considered? Earth is not lacking in organisms capable of surviving in seemingly uninhabitable environments. They are called extremophiles, organisms that can survive and thrive under conditions so extreme that most other forms of life could not endure. The existence of extremophiles challenges our definition of what conditions are truly necessary for life. Instead of searching only for life on planets with stable temperatures or liquid water, we have begun to expand our search to extremely harsh environments. Heat-loving organisms are a clear example. They can live in boiling hot springs where temperatures can reach nearly 100 degrees Celsius. In such places, water is not the only environment for life. High temperatures and strong acidic chemical reactions are the factors that enable life to develop. Could it be that in hydrothermal vents on planets such as Mars or Europa, life could arise in such extreme environments? The answer may be yes, if organisms are capable of using hydrothermal chemistry as a source of energy. Another fascinating example is salt-loving organisms. They live in hypersaline lakes where the salt concentration is 10 times higher than that of Earth's oceans. This raises an important question. Could life exist in the subsurface oceans of Europa, where the salt concentration is believed to be extremely high. Halophilic bacteria on Earth have developed the ability to adapt to such harsh environments, and they may serve as models for extraterrestrial life under similar conditions. One of the most striking examples is Deinococcus radiodurans, a bacterium that can withstand extremely high levels of radiation. It can endure radiation doses thousands of times higher than what humans can survive, and can repair its DNA after being damaged by radiation. This makes it an ideal model for studying how life could evolve in environments with intense radiation, such as the moons of Jupiter, where radiation levels are extremely high. Could extraterrestrial life develop similar protective mechanisms to survive in the harsh environments of space? While we search for life in environments of extreme heat or intense radiation, another story of extreme life hides deep beneath Earth's oceans. The Hadal Zone, the deepest region of the ocean, is where pressure can be hundreds of times greater than at the surface. Here, tiny organisms such as microbes and crustaceans thrive despite the pressure and harsh conditions. What is remarkable is that organisms living in the Hadal Zone have developed biochemical mechanisms to prevent the breakdown of proteins in cell membranes under extremely high pressure. Could similar organisms be found beneath the icy surfaces of planets such as Europa and Enceladus? Where deep oceans lie beneath thick layers of ice, enduring extreme pressure and freezing temperatures? Scientists believe that life in such environments could resemble the organisms living in the Hadal Zone, where living conditions are vastly different from those on Earth's surface. The study of extremophiles and the Hadal Zone not only helps us understand how life can exist in extreme environments on Earth, but also expands our perspective on life beyond the planet. And discoveries about extreme life have completely changed the way we perceive life in the universe. Life does not have to depend on traditional elements such as liquid water and oxygen. Life can develop in any environment that contains liquid and energy. Experiments on microorganisms in space, along with research on the Hadal Zone and extremophiles, have shown us that life is not a rare phenomenon that exists only on Earth. If organisms can survive in extreme conditions on Earth, then extraterrestrial life could also develop in environments we have never imagined. These questions are no longer hypotheses, they are now the goals of modern space exploration. The journey to search for life beyond Earth has taken us across distant, unexplored regions of space. From the frozen oceans on Jupiter's and Saturn's moons, Europa and Enceladus, to places where methane and other organic molecules could serve as solvents for life. At the same time, advanced technologies such as the James Webb Space Telescope have allowed us to look deep into distant exoplanets, opening up unprecedented possibilities in the search for biological traces. Recent discoveries have proven that life is not a rare phenomenon that occurs only on Earth. These data are no longer mere speculation, but concrete evidence, revealing that life could exist in many places throughout the universe. Discovering life beyond Earth is not simply about finding bacteria or simple organisms on other planets. More importantly, it is a process of redefining the nature of who we are. If life exists on another world, even as bacteria beneath ice, or as organisms living in liquid methane, it would prove that life is not a single random event, but an inevitable product of cosmic physics and chemistry. We will continue this journey not only to search for life, but also to gain a deeper understanding of our place within this vast universe. The search for life beyond Earth continues. The discoveries we have made so far are only the first steps, yet it is undeniable that the existence of life beyond Earth is merely a matter of the near future. Opening a new chapter in our quest not only for life, but for a deeper understanding of the universe's true nature and its infinite possibilities. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.